just a couple of household items. You should be able to hear me. Audio is provided over the internet. Make sure your speakers are on. I think we've set it up so that everybody is muted, so you don't have to worry about that yourself. If you have any questions throughout the webinar, please ask them, and we do that through the question panel on the right-hand side of your GoToWebinar interface. You'll see an area where you can type a question. Whenever I see a question, I will go ahead and answer that. So okay, let's get started. All right, so welcome to this webinar on layer protection analysis with Lopa X, and we're working on integrating that entire safety lifecycle. So this is kind of exciting to see how some of the different functionalities in our next generation, the exSILentia software, will work together. And we'll look at that in the webinar, and we'll see a little bit of demo as well. My name is Iwan van Beurden, and I'm Chief Technology Officer, Director of Product Development at exida. I do a variety of things with regard to end-user services. Think IEC 61511, ranging from the facilitation of PHAs all the way to site acceptance testing, witnessing functional safety assessments. I work with our manufacturer customers in evaluating their development processes and their products in compliance to IEC 61508, and I get involved with our certification activities as well. My main reason, of course, for talking to you today is because we have a new product, Lopa X, that we released, and I'm responsible for the development of our end-user software, which is exSILentia as well as SILstat. Member of ISA 84, and as I said, there's a variety of tasks that I perform as part of my daily duties. In the webinar, we are going to talk about what layer protection analysis is. So a little bit of background as to what is layer protection, what type of requirements are there when you call something an independent protection layer. What does that mean? Then we're going to introduce the Lopa X tool. We're going to talk about how we are integrating the safety lifecycle, and then we'll wrap it up with the Lopa X tool in action. And again, any questions, feel free to type those into that question section on the right-hand side of your screen. So, what is layer protection analysis? It is a risk assessment method that we use typically to determine the needed risk reduction factor. Sometimes we will use this method only after initial qualitative methods have failed / haven't provided detailed enough results that we're really looking for. Sometimes we trigger doing a layer protection analysis based on the consequence severity. So if we have something that is really bad, we try to protect against that. We really want to know how often does this accident happen. So if we have an explosion of a boiler and we potentially kill a couple of people, how often is this really going to happen? We deal with initiating event frequencies. We look at failure and success of different protection layers, and we look at a tolerable level of risk or tolerable frequency for a particular type of event. And with the layer protection analysis, we can evaluate the amount of risk that is in the process in a really quantitative method. Sometimes we simplify it a little bit. You could call it a semi-quantitative, but typically when we are diving into the layer protection analysis tool and methodology, we are doing a quantitative evaluation. And it helps us to determine if there is enough protection for potential process hazards. And here we have an overview of typical layers of protection. and you see a vessel on the right-hand side with a certain chemical, a certain material, made of a certain material. There's a pressure, a temperature, and a certain volume within that tank, and that is basically the first layer of protection. If we are concerned with the overpressuring of that particular vessel, the process design itself could help us in limiting the overall frequency that that event occurs by limiting the inventory. There may be process control, and that's the green layer. Let me see if I can if I can point that out. Well, you can see my highlighted cursor here. The green layer, process control. Obviously, we're trying to keep the process within the normal operating limits. We may have an operator intervention through an alarm, and here we have a high trip point that will initiate an alarm. And if that fails, we may have a safety instrumented system that will provide enough, will bring the process to a safe state when the hazard is occurring. If that doesn't work, we may have active protection. Think of the relief valve, which is on the right-hand side here. And if that doesn't work, we may have some passive protection, like a dike that is built around the vessel. And then if that fails, there may be a planned emergency response and or a community emergency response. So those are some typical layers of protection that we see in a process. Now, when we evaluate the frequency or the probability that a hazard occurs, we look at all these different layers of protection, and we can see that those hazards can be prevented by the effective working of those layers of protection. But we need to realize that those layers of protection have holes. They aren't perfect. And when those holes align, a leak, as illustrated here, could result into a problem. So we need to make sure that the barriers are adequately implemented, but the holes, that could be problems with the barriers themselves, or a incorrect human action. But if we look at what Lopa does, we basically start out with a initiating event with a certain frequency, and then we account for these different layers of protection, realizing that they are not perfect, they may fail, but that initial frequency of that initiating event will end up being a much lower accident frequency due to those layers of protection. So if on average a control function fails once every 10 years, you typically are not blowing up boilers once every 10 years. But why does that happen? There may be layers of protection. The control function may still fail once every 10 years, but an operator may take an action, or you may have a relief valve, and so on. So these protection layers end up reducing your accident frequency from that initiating event frequency, and that's what's also illustrated here in the image, where we have that initiating frequency with a certain size and ending up being a much lower frequency at the end. Now, when we talk about these layers of protection, we need to see as to how effective are they, and we use the Swiss cheese here to show layer of protection effectiveness. On the left-hand side, you will see a layer here that is very ineffective. There are 100 holes out of 100 possible holes, or in other words, it will always fail. Its probability of failure is equal to 1. That would somewhat correspond to, let's say, a SIL 0. There's just simply no protection from this layer. Now, it's still important to identify the layer and at least document that you've considered that layer of protection, but at the same time document that you consider its effectiveness to be nil. So that for future reference, people say, oh, they did think about that, but for whatever reason they didn't think it was effective enough. The second one here, the one that I draw a square around, that has 10 holes out of a possible 100, or in other words, a probability failure of 10%, 0.1. That's roughly equivalent to a SIL 1. And then the third one, we see one hole. The triangle one, we see one hole. Probability of failure is 1 out of 100, or 0.01. That's roughly equivalent to the same amount of protection that you would get from a SIL 2. And then all the way to the end, we see the probability of failure. That's the second circle. Probability of failure is 0 because there are no holes, which would mean that the layer of protection is perfect, will always mitigate the hazard. Now, I don't tend to believe in perfect. I don't tend to believe that we will have a probability of failure that is equal to 0. So I would like to even consider maybe 1 out of 1,000 or maybe 1 out of 10,000, but at least say, hey, nothing in life is perfect. People can make mistakes. Obviously, the more barriers you have with the lower number of holes, the more unlikely it is that those holes will line up and that your hazard will occur. So that will really reduce that initiating event frequency to something that is more acceptable. So when we talk about protection layers, there's a couple of things that we need to keep in mind. Those protection layers need to meet 4 distinguished attributes. They need to be specific. So when we classify something as a layer of protection, we really need to make sure that that layer can detect the hazard and bring the process to a safe state. It really needs to be able to, in the ideal world, completely negate the hazardous event. Obviously, it's not ideal. There's a probability of failure, but we tend to not look at, oh, it's partially effective. No, it will prevent or it will not. Then the layers of protection need to be independent. It's kind of in the name already. We tend to refer to these as independent protection layers or independent layers of protection. Why do they need to be independent? Because when we account for a layer of protection to fail, we assume that layer will not impact any other layers of protection. So a failure of one layer will not cause a second layer to fail. If that is the case, then we just need to consider those 2 layers as one, and we need to do a little bit more detailed analysis. The typical example is you have a control function, assuming the control function is not the initiating event. You have a control function that measures process value, performs a pre-configured algorithm, and drives a control valve. And you can say, well, the control function is a layer of protection. Oh, and by the way, I'm also alarming to an operator, but that alarm is based on the same the same process measurement, the same controller, and basically what you have is a more complex layer with just 2 separate fine elements. One is the valve and one is the operator taking action. So instead of saying, hey, I have 2 layers, what you need to do is you need to say, hey, I got only 1 layer, but the final element is a little bit better than just a single final element would be. You got diverse final elements. The protection layer needs to be dependable. It needs to be always there. The protection layer, you're relying on it. If it's an operator and the operator makes rounds and the initiation for the operator is only in the control room, I don't know why it's flipping to the next slide, and the operator is only in the control room, then or the initiation is only in the control room, then you need to really wonder if that operator can reliably prevent the hazard from occurring. So the layers need to be dependable, and then finally they need to be auditable. In other words, you need to be able to test the layers. You need to train that operator and make sure that the risk reduction that you assume for these layers is continuously achieved. So it's similar as when you talk about a proof test for safety instrument function. You kind of need to make sure that your layers of protection, that they are adequate and that they are that they're still functioning, that there are no dangers or detected failures in them. So when do you use LOPA? Well, typically after your hazard scenario has been identified, and typically after an initial qualitative hazard evaluation has been done. So typically you do your process hazard analysis, and you may come to the conclusion that certain potential events, certain hazard scenarios are very low probability, or low likelihood to occur, a low consequence, low severity, and the risk is something that you simply tolerate. Maybe your typical slips and trips. Okay, someone may get injured a little bit, but it doesn't happen that often. On the other hand, there may be some scenarios where you say, well, that may happen a couple of times in the life of the plant, and you know what, if it happens, we're really going to hurt somebody. And we want to look at that in a little bit more detail so that we know what the actual frequency is of the, this is going to happen a couple of times in the life of the plant. So criticality is a trigger for LOPA. So when you're dealing with severe consequences, in some cases regardless of likelihood. So if you are really going to hurt individuals, you may just want to look at it in a little bit more detail instead of the simple risk matrix or risk graph approach. Or if it's really a high-risk scenario where the consequence is high, the likelihoods are expected to be high, you really want to understand what's going on. Another reason to do LOPA is when it's just simply too complex to predict what the frequency is of the initiating event, and taking into consideration some of the layers of protection. We tend to not have a number off the top of our heads where we can say, hey, the boiler or the control function will fail, the pressure relief valve will fail, the operator will fail, and we tend to not really know what the typical frequency is of that. But we do know what the individual frequencies are of the control function failing, as well as the typical probability of failure of those protection layers. So if a initiating event is really complex, and we can split it up into smaller pieces, and it's typically easier to get data for the smaller pieces, and then determine what the complex event frequency is. So that's reasons to do LOPA. At some companies, they tend to kind of do LOPA all the time. Need to be a little bit careful with that. It's absolutely a good approach. But it can be very time-consuming. Now, you could argue, to do a detailed analysis, and if that detailed analysis suggests that you need a SIL 1 instead of a SIL 2, and thereby you save, you save a valve, so to say, and that may, pay for the extra effort that you go through. But it can be a little bit more time-consuming than the quick and dirty risk evaluation that you may do as part of a hazard. So let's start with, that is a little bit of a background on layer protection. So now let's talk about our LOPA tool, our Lopa X tool, and it's a layer protection analysis tool. Obviously, that's given in the name with the intent to be used by process safety control engineers in support of plant management and operations personnel. So that's a typical Lopa tool, and it allows you to evaluate a hazard scenario consisting of one or more initiating events, and we'll look at that, what that means. It allows you to specify enabling conditions, multiple independent protection layers, multiple and conditional modifiers, multiples of those as well. And it allows you to specify the effectiveness of each of the enabling conditions, IPLs, and conditional modifiers on a per initiating event basis, as well as a severity category basis. And depending on fact, if you have specified a risk tolerance, the Lopa tool will actually also be able to calculate resulting risk reduction factors, or if you identify something as a potential layer of protection, and you want to know potential safety instrument of function, for example, and you want to know how much risk reduction that safety instrument of function needs to provide, you can calculate that as well. And I will show that to you in a little bit. I have a detailed question here. Well, I got two questions here, so let me address those real quick. The first question is, do I always need a HAZOP analysis before performing a LOPA? Not necessarily. The advantage of doing the HAZOP first is the HAZOP really helps you understand the process. It really helps you understand what the layers of protection are that are in place. Now, if you have that information available through a different method, then you do not need to do a HAZOP study. You could theoretically start out with the LOPA. But we will see, and in the remainder of the webinar presentation, you will see that it is really it's really something where a lot of information comes out of the PHA. So it's quite useful to do that PHA first. Another question that's really specific: if I have two pressure relief valves set at the same pop-up pressure, can they be considered as two separate layers of protection, or should they be considered as one layer of protection? If you assume that they are both capable of preventing the hazard, and that there isn't really any correlation between the two, that you could argue they're similar designs, you could probably consider them separate. I would tend to consider them as one layer of protection, one out of two, with a common cause factor. That's a little bit more conservative, and of course you need to make sure that each relief valve is sized large enough so that they can actually prevent the hazard from occurring. But I would tend to go with a one out of two approach and a common cause, which is going to help you significantly, but it's a bit more conservative. Yeah, and here's a clarification here on that question. 100% rated to prevent the hazard consequence. Depending on they have the same physical environment, they're in contact with the same process. I may be inclined to consider a little common cause there, just to be on the safe side, instead of saying, hey, they're absolutely 100% independent, simply because of the similar design and environment. All right, so here we look at the Lopa X worksheet, and what you see is multiple initiating events. So let me get my highlighter here. Multiple initiating events for the same hazard scenario. In this case, the hazard scenario is the brittle pipe fracture on the warm end of a cryogenic, has a typo here, separation. We see a flow imbalance between streams as an initiating event and a weather extreme. With different frequencies, we can see that here, different frequencies, and some enabling condition here, and some IPLs, and we'll talk about that in a little bit. Then, as I mentioned, the tool will allow you to account for different levels of effectiveness for your enabling conditions, your IPLs, your conditional modifiers, on a per initiating event basis. So the top screenshot may actually show that a little bit better. We see two initiating events, and you see that steam drum relief valve A, in this example, is effective in protecting against the first one, but apparently not against the second one. And this is a made-up scenario, just so you can see the difference. But you can see, hey, I got that IPL listed, and that IPL is apparently effective in protecting against the first initiating event, but not the second initiating event. You can also see that here in the more detailed screen. You see it being effective here and not here. So you can account for effectiveness levels on a per initiating event basis, and you can also look, and I'll show that to you probably in the demo. portion where we have multiple risk receptors or multiple severity categories, in this case business, environment, and safety, and I can indicate that in this case, relief valve is effective in protecting my business interests, my safety interests, but apparently it is not effective in protecting the environment. So let's say I'm releasing to the atmosphere, and thereby, it would not be effective. So I can indicate if a protection layer is effective, or an enabling condition or conditional modifier, if it's effective for all initiating events, for what severity category, and a tool allows you a lot of flexibility that way. So for those of you that are familiar with exSILentia, exSILentia 3, exSILentia 2, exSILentia 1, we have a select tool, and the SIL selection is it's kind of a combination of layer protection analysis and SIL selection. What we've done with Lopa X is we've kind of pulled the layer protection analysis concept out of the select tool and made that a separate tool. That way, you can determine just frequencies if that's what you want to do, or you can determine risk reduction required, which will then feed into the select tool to perform your SIL selection to determine what target SIL level you need. So in the tool set as we move forward, the layer protection analysis portion is pulled out of the select tool, and the SIL selection is really just that, a SIL selection process where we determine what the target SIL level is based on the risk reduction that is calculated. There was another question. Let me find that real quick. Where is it? I must have done something wrong here. All right. Anyway, the question was related to if layer protection, if our Lopa tool considers multiple initiating events for each hazard scenario, and the answer is it can. It doesn't have to. It's up to the user. You can decide if you want to do it one initiating event or if you want to consider multiple initiating events. We will see that the process hazard analysis tool will allow you to determine hazard scenarios, and those are the basis for the layer of protection analysis. And those hazard scenarios, you can put in as many initiating events, or as many causes as you want, which could be one or which could be many. So what happens if if you have multiple initiating events for the same hazardous scenarios that are not independent? That goes into what are the frequencies that you're assigning to those hazardous scenarios. Okay, and then there's another question here, a very good question is, well, what if you don't have data for these protection layers? What if you don't have initiating event frequencies or probabilities of failure? We are finalizing a database. So for those of you who are familiar with exSILentia, that are familiar with the Silver tool, one of the strong points of the Silver tool is the embedded equipment database. We're finalizing a layer protection analysis database where we have initiating event frequencies, typical initiating event frequencies, and typical protection layer probabilities of failures that you can select from. There is third-party data available. In some cases, you might find something in the process equipment reliability data PERT information from the Center for Chemical Process Safety, that's a CCPS, which is part of the American Institute of Chemical Engineers, ASCG, or there is a book that was written by a gentleman called Lees, L-E-E-S, that's called Loss Prevention in the Process Industries, that has some data on protection layers, and then the standards have some data on protection layers, and best of my knowledge, the CCPS is about to release another book with typical protection layer and initiating event frequencies. But we're finalizing a database that we will be supplying with the tool as well. So yes, Select and Lopa X are two separate modules, but they're still part of the same exSILentia platform. Now you can, I didn't show any of the overall exSILentia options in the presentation. You can buy just the Lopa tool and just do layer protection analysis. Some customers aren't really interested in SIL levels. They just want to do likelihood evaluation, and they may be looking at different criteria than safety integrity levels. But they work together to help you determine the SIL level when we talk about the process industry. All right, so we've seen some of the screenshots, but now let's talk about the entire life cycle, because the entire safety life cycle is a little bit bigger than just layer protection analysis. And if we look at the safety life cycle, we see in a simplified format, we see the three phases: analysis, realization, and operation. And assuming that everybody's familiar with the exida products, the exSILentia software kind of covers the analysis and realization phases. It does the process hazard analysis, the layer protection analysis, and SIL selection, the safety requirement specification, and we split that up into a process SRS and a design SRS, a SIL verification module, proof test generation or proof test definition for use later on, and as well as alarm rationalization. So those are all tools that tend to happen in the early phases of the lifecycle, analysis and realization. And then during operation, we have our SILstat software, our live event recording software that you can use to record proof tests, to record failures, to record demands, and so on, and successive failure of layers of protection. Information, obviously, that you want to collect to eventually feed into your layer of protection analysis. The alarm rationalization, though, the actual work, alarm rationalization work tends to be done as part of the analysis and realization phase. The alarm tool actually also works in the operation phase as an audit tool to make sure that the alarms haven't been modified. So you could kind of put it in the operation phase here as well. But when we talk about our next platform, or exSILentia, one of the things that you will see is we'll have a framework that will support several different modules. And there are different licensing options, and we're not talking about that right now. But you can have a process hazard analysis tool, you can have a layer protection analysis tool, Select, SRS, Silver, proof test, and alarm rationalization tool. They all work on that same platform. And because they work on that same platform, depending, regardless of the licensing that you have, whatever modules that you have licensed, it shows up as one integrated, one single tool. And one of the things that's neat about that is that if you do your process hazard analysis using our PHAx tool, you'll define causes, you'll define safeguards, you'll have consequence with certain levels of severity, and you can assign those to a hazard scenario. And then when you want to evaluate that hazard scenario, those causes are initiating events. Those safeguards could be independent protection layers or enabling conditions or conditional modifiers, depending on how you do your PHA. Sometimes people include those in the safeguards, sometimes they don't. Your consequence severity level will dictate applicable tolerable frequency of that particular event. So stuff out of the PHA will help you populate, help you dictate what the layer protection analysis is going to look like. The layer protection analysis, your independent protection layers, may determine that something needs risk reduction, or that you need to have a certain risk reduction factor for safety and instrumental function, and that will feed into SIL selection and subsequent the safety requirement specification, SIL verification, proof testing. You may have identified alarms, and those alarms will go into the alarm rationalization. So, as you see the single tool, all that information. All that information will be nicely transferred to the next phases. What I didn't put on this slide, but what is a good thing to highlight is that our SILstat software, we are seeing that as a separate. Well, obviously it is a separate product, but we see that as a separate tool simply because that tool is active throughout the life of the plant. and you know, your PHA and SIL selection, SIL verification, etc. That's really a project-based tool. Now, you may work on it one unit at a time, for example. But the information that you collect here in the exSILentia tool is then transferable to the SILstat tool. So if you've defined your safety and semantic functions here, if you've defined your hazard scenarios with your different IPLs, all of that information is transferable to the SILstat tool, at which point you can you can basically look at different protection layers and classify their success and failure. As I talked about that a couple of webinars ago when I talked about SILstat. You know, the sequence of IPLs is something that that you can specify here, and that is transferable to the SILstat tool. So that was a good comment. So let's look at an example. So we have a process hazard analysis where we look at a compressor suction drum, 25V101, and you know, the objective of that drum is to eliminate liquid in the feed to compressor 25K101. So that compressor is up here. Oops, did I get my highlighter? Yeah, I did. The compressor is up here. For whatever reason, my highlighter is not working. Let's see. Let's try again. No. I got another question that's very good. Sorry, that's why I was distracted. But let me see if I can get that highlighter to. Oh, there we go. Oh, there was some delay. I'm not sure if my internet was having issues. But here's that compressor. Here's the vessel or the knockout drum, the suction drum that we're protecting, and there are some functions around it. All right. So that is that's our basis of the tool or of the concept. And then, you know, we've done a process hazard analysis where we've identified a couple of causes, which are your initiating events, at least in the action terminology. We've identified safeguards, and those safeguards, those could be IPLs. So there's a lot of information here that is very useful when we get to the layer protection analysis. And that is kind of the worksheet that you see here. Here's the layer protection analysis for that particular scenario. Compressor, suction drum, high level, and we see multiple initiating events with different frequencies, with different IPLs, and actually see how we can calculate a required risk reduction. And the transfer of the data just happens with one click of a button. So I have a question here, and that is it possible to connect the PHA and the Lopa so you perform one analysis as a whole? And yes, it is. You know, we see them as two separate phases, but as if you go through the tool, we'll see that once you define something, it's immediately available in the next phase of the life cycle. And then there's another question here, if I could repeat my example before. Let's see if I can show a, no. I was trying to see if I could show a quick drawing. But the example that I mentioned before, this was when the layers of protection were not independent. The example was related to, I have one measurement. That one measurement goes into the control function, or in the control system, I should say. And then based on that one measurement, I'm either operating a valve, or and at the same time, I'm sending an alarm for an operator to do something. The operator action is based on the same process value measurement as the control function action. Therefore, they are not two independent layers of protection. They have common equipment. And you would need to consider doing a detailed evaluation on that particular protection layer, combined protection layer of the control valve and the operator action as a result of that process value. So because they're responding to the same measurement and the same kind of signal generated by the controller, you cannot consider them two independent protection layers. And I'll try to get a slide in for this afternoon session. As you may know, there's an afternoon session where I will show that. So that's an example. So let's look at layer protection analysis tool in action. So what we want to do is we kind of want to look at what I just showed on the slides, review compressor, suction drum, PHA worksheet. Then we want to transfer the data from the PHA to the Lopa worksheet. We want to assign frequencies, and then we want to calculate the risk reduction for a proposed SIF. So let's have a look at that. So I am going to show you the process hazard analysis worksheet, and it looks like everybody can see that now. I'm sharing my screen. So here we have in the cryogenic separation, on the note is the warm end cryogenic separation. We have a we have a couple of different deviations, and one of those deviations is high level, and that's the one that I have a PHA worksheet for. So let me collapse this part here. And in that PHA worksheet, we see here on the left-hand side, and let's see if my highlighter works here. We see here, yeah, we see causes. Two causes were identified, and then those are two causes that were identified, both with the same consequence. There's a severity category assigned to them with different severity levels. In this case, in the example, resulting in levels of risk. Then next, we see safeguards identified, alarm, an operator response, and a process trip, and we see an independent PLC low temperature trip suggested as well. Am I looking at the right one? Oh, I'm looking at the wrong, I think I'm looking at the wrong scenario. Hold on, my bad. There we go. That is better. I was looking at the wrong scenario. Apologize for that. So here's my cause, where we're looking at the compressor scenario. My bad. Here's the cause. Two causes were identified. The consequence, severity levels, likelihoods leading to risk. We have safeguards identified. And then one of the things that we see is that the drum level controller is identified as a safeguard for the second cause, which is excessive amounts of liquid in the drum inlet gas, but not for the first cause. Why? Because that level control loop is the one that's failing. So that cannot protect against itself. Then we see some recommendations, and one of the recommendations is consider a high-level SIF. Then all the way to the right, you see, yes, we want to do a Lopa, and then this radioactive symbol says, say, there's a hazard scenario, and that hazard scenario is a compressor suction drum high level. And that hazard scenario is assigned with this first cause-consequence pair as well as the second cause-consequence pair. So everything that you see here on the PHA worksheet is related to that same cause-consequence. Is related to that same hazard scenario. Now, they do not necessarily need to be on the same deviation worksheet. They could be, you can assign stuff that's on different deviation worksheets. But in this case, I kept it simple, and everything is on that first sheet. So that's the first step. Let me see, there's another question here. I will address those questions. There's a couple of questions here that I will address shortly. I think that it makes more sense to address those in a later date. So let me go on, and so the first step in the first step was to review that PHA worksheet. Now we want to transfer the data to the Lopa worksheet. So we're going to go to the compressor suction drum, and as you can see, that Lopa worksheet is currently empty. Empty except for one thing, and that is up here. There's a target frequency, and that target frequency is obtained from the severity selections, or will be obtained from the severity selection. So default is 1E minus 5, and we'll see that that changes as soon as we transfer data over from the PHA. And there's two buttons on the worksheet. One is transfer everything from the PHA to the Lopa, so all hazard scenarios. Or the second one is transfer data on one hazard scenario at a time basis, which is what I'm going to do now. So when I click this button, the first thing is this will I get a warning that the data will be merged from the PHA into the Lopa. Do I want to continue? Warning is telling me if I would have anything in here, it would be basically removed. So yes, I want to continue. And then the second question is, do you want to override the existing target frequency with the target frequency based on your PHA? So I hit yes as well. So what we see is that my severity, as I selected in the PHA, apparently dictates a target frequency of 1E minus 4. All right, so that's the starting point here of my Lopa. I can then specify. Hold on, let me take a step back. You see the initiating events; those were the causes that were specified. You see frequencies. So at this point, I need to assign a frequency to each of these two events. And then you see the IPLs. So we have an alarm and operator intervention, we have occupancy, and we have the drum level controller. And I can indicate which ones are effective, protect against the different initiating events. So first, let me just say the controller fails once every 10 times, once every 10 years, I should say. And let's say the excessive amount of liquid happens twice a year. Just coming up with some numbers here, and what that shows me right now is that the overall frequency that this event will happen, not accounting for any protection layers, is 2.1 times per year. I can only tolerate it once every 10 to the minus 4, once every 10,000 years. So the next step is that we have these different protection layers, and we can assign probabilities of failure to those protection layers. So let's do that for the alarm and operator intervention. In this case, I'm going to use a 0.1 probability of failure of 10 for the alarm. The drum level controller, same thing, probability of failure is 0.1. And let's see, the occupancy, let's say the area is occupied only 50% of the time. So those are the specification that I've done for these particular layers of protection, imported as IPLs initially. And next, I need to indicate if they are effective for the different initiating events. So in this case, the operator, yes, he's effective for both cases, the control loop failure as well as the excessive amount. The occupancy, you could probably call it a conditional modifier instead of an IPL, but I'm going to leave it here for now. We can put that frequency in, and then finally we have the drum level controller, which is effective in protecting against the excessive amount of liquid, but not in protecting against the controller function failing itself. So those are the different IPLs classified for these initiating events, and I end up with a frequency of 1E minus 1.5E minus 2. I can tolerate it 1E minus 4. Obviously, I need risk reduction. That is not a surprise. We saw that coming. So if I go back to my slide real quick, yeah, I assigned initiating event frequencies. So one of the things that we saw in the recommendations is that the recommendations suggested we should consider a initiating event frequency, a safety instrumental function. So one of the things I can do here is I can add another IPL. And let me name that IPL potential high level SIF. And that SIF, or that function, will be effective in protecting against both initiating events. So I link it to both initiating events. The default probability of failure is 1, assuming that it always fails. And I would have to put in a probability of failure and see if, let's say I say 0.01. Let's see if that's sufficient. In that case, I still end up with a risk reduction factor that I need. But I can also ask the tool, so in this case it will be equivalent to exSIL2. I can also ask the tool to calculate it for me. So instead of me specifying what the probability of failure is, I can say, well, tool, why don't you calculate it for me? And oops, there you go. When I do that, you can see that the tool says, well, in order to protect against these two initiating events, and get a target frequency of 1e minus 4, actual frequency is 1e minus 4, no residual risk reduction, we need to provide a safety instrumental function with a probability of failure of 6.67 e minus 3, which translates, and we need to do some rounding here, but which translates to, let's say, a risk reduction factor of 150. If we can implement that, then we have adequate risk reduction. So there's two things I can do with the Lopa tool. I can either just end up with a resulting frequency, this actual frequency at the top here, and I'll make sure that you see that, and that is an input into my SIL selection, or I can indicate, hey, I need to calculate a safety instrumental function in the Lopa and actually determine the required risk reduction factor, at which point that is an input to the SIL selection. Now, I showed that this information was transferred from the PHA tool. So now let's say we want to change something here, and I think that's one of the neat features of an integrated tool. So in this case, I have a drum level controller, 25 LC101, and then I'm just going to type some extra characters here, webinar information. Hope I didn't make any typos. And now let's go back to the PHA. And what we see in the PHA is for that particular safeguard, right here, the words webinar information are added. So it's the same entity. It's the same. It's the same item in the library within the tool. Any changes I make here are automatically made everywhere where that same item is used. So that's a neat thing. If I would come over a spelling mistake or I want to clarify something, I can do that right here. So that's in a nutshell the layer of protection analysis method. I saw there's a couple of questions, so let me try and address some of those questions. Oh, even more questions. Good, I like it. So one reference, one comment with the example that I created before when I said the control function and the alarm are a combined layer of protection. That, of course, is only true if the control function failure of the control function is not the initiating event. So in my example, what I was talking about, it was not the control function failure was not the initiating event that I was protecting against. If it would have been the initiating event, then absolutely, we cannot consider the control function and the operator, for that matter, because they're relying on the same process value, as a layer of protection. So make sure that independence as well, not just from a layer of protection perspective, but also from a what's the initiating event versus what am I protecting against. And that's kind of what I showed here on the screen, where I have the controller being a protection layer for the excessive amount of liquid, but not being a a layer of protection for the control function failing itself. There is another question here: can we import a third-party PHA worksheets into exSILentia PHAx? Absolutely. We have import capabilities. One of the things that I've noticed is that when we create a import function, we tend to do that for the typical worksheet that you would use. When you make any changes to that worksheet, the import tends to not always be as successful. But having said that, talk to our support staff at exida, well, support.exida.com. Talk to our support staff, and we can typically, even within the development environment, tweak the importer so that it will work with your customized worksheet. So yes, we can import out of third-party PHA tools. There's a question here as a reference for occupancy as an IPL. I don't have a reference per se, but what we typically look at is impact zones or effect zones. So if an event occurs, how many people are there within, for lack of a better word, the kill radius, the injury radius, or outside? And sometimes, I had a scenario where there was a vessel that was not designed to withstand the original pressure, or the pressure that could occur within that vessel, and that vessel was next to the break room. And in the break room during lunch there could be 10 people, and we came to the conclusion that if that vessel would go, the pressure wave was so high that it would basically knock down the wall in the break room and potentially kill everybody that was having a lunch there. We came to the conclusion that we needed quite a lot of risk reduction because high severity event. At the same time, that lunchroom was only occupied maybe 1 hour out of 24, or maybe 2 hours out of 24. So there's 22 out of 24 probability that when that event occurs, there's nobody in that area. So that's an area, that's a scenario where you can account for occupancy. Can we add multiple independent CIFs as IPLs for the same hazard scenarios? Yes, you can. In this case, and I would have to go back to the libraries. Here's my safeguard library. Here you see my high level CIF. Let's see if I can open it up. Not right now. Okay. I'm looking at the wrong screen, I think. Oh, here we go. Here we go. It's presented here. Here I can indicate that this is indeed a safety instrument function, but I can I can add a second safety instrument function to this scenario. So I could add an IPL. I can say this is, for lack of a better term, CIF2. I can say this is a SIL1 safety function. Maybe a little bit confusing. CIF. Oh, my bad. Wrong keys. CIF B, SIL2, and sorry, SIL1. That's the probability of failure that I put in, and I could just simply say, hey, this is the probability of failure, and this one, maybe I need to recalculate. Let's see. Oops. How do I? This one, I may want to just simply hard code. Hey, we want a risk reduction factor of I don't know, 15 or so. So that is an approach that you can do. Again, make sure they're independent. If they go through the same logic solver, make sure if it's SIL1 and SIL2, make sure the logic solver is capable of handling that. Maybe you have two completely separate functions, maybe one through a triple arm, one through a logic solver, but make sure that that's the case. Why is there a separate tool for SIL determination? That's a very good question. The majority of our customers will be using the layer protection analysis tool. The majority of our customers will be using this tool to determine the amount of risk reduction factor, amount of risk reduction that a safety instrument function will need to yield. If you use this tool, then yes, from the risk reduction factor, you can immediately determine the SIL level, and you will see that the SIL selection tool is going to be a very simple tool at that point. You just say, hey, this is the SIF, this is the required risk reduction, therefore this is the SIL level, and it's not really that exciting. There are some customers that use a risk matrix or a risk graph to do their SIL selection, and in those cases, the initiating event frequency out of the Lopa is an input, and is an input into their diagram. So in that case, you kind of need a separate tool to handle that. But absolutely, the key information, frequency of the initiating event comes out of the layer protection analysis tool. So another question here, what's the difference between the intermediate frequency and the actual frequency? Well, if you only have one initiating event, the intermediate frequency and the actual frequency are the same in this calculation. In the scenario here with two initiating events, you will see that the actual frequency is the sum of the two intermediate frequencies. So that's the difference there. Someone has lost audio. I didn't do anything on my end, so I hope that is fixed by now. So as you saw, data from the PHA was transferred to the Lopa tool. In the same format, data from the PHA and Lopa is going to be transferred into the safety requirement specification tool and into the Silver tool. So this one platform with multiple modules will transfer your data seamlessly. Now, yes, in this case, you need to click the button to transfer the data. We want it to be a user action to do that. But absolutely, PHA information is going to be available in your SRS, going to be filled in automatically where applicable. Operator presence, in some cases, people assume it must be at least less than 10% of the time. And sure, if you want to consider your IPLs each as a full order of magnitude, absolutely, they need to be 10% of the time. But if you do a full quantitative Lopa, you don't have to stick with these round numbers. You can account for, in this case, 50% of the time the area is occupied, or 33%. You take it into consideration. It's not going to solve a whole SIL level, but maybe in combination with other layers of protection that may not be 100%, one order of magnitude, I should say, effective. It may end up being an order of magnitude. So the prescriptive requirement that an operator presence must be less than 10% of the time, that's only applicable if it immediately leads to a SIL level result. So you see that in a risk graph, for example, where you have this occupancy parameter and the difference is a whole SIL level. In that case, yes, it needs to be 10% of the time. There's another question here, gentlemen, that, let's see. Is it possible to evaluate the SIL of an existing SIF? Yes, that will be done in the SIL verification tool. In this particular example, I have only safety as a scenario. There's a question here: can we add environment and business? So I'm going to close this file. I'm not going to save it because I want to use it this afternoon as well. So I'm not saving it. And then I think this is the function that I played with yesterday. Here you see the option up on top, individual versus multiple. In this case, we have multiple risk receptors: business, environment, reputation, and safety in this example, and you can see them all in one spreadsheet. Or if you would like, one worksheet, you could say, well, now I want to look at business, now I want to look at environment, now I want to look at reputation, now I want to look at safety. So we can combine it in one diagram, and you can indicate if a layer is effective for all risk receptors or not, And when we go to safety, we will see that the first one is not effective, the second one is. So if we go to individual, yes, that's exactly what I just configured. So you can see it in one one sheet if you want to. And that's, again, that's, some users like it that way, some users don't. So that's why we have the individual mode where you switch between them, or you have the multiple mode where you do everything at once. Do you consider operator intervention and the alarm as one protection layer? Yeah, they're usually one layer, because it's the alarm that triggers the operator action. Otherwise, the operator doesn't know what to do. So the operator is really the final element of the alarm. So that's why it's, you know, I would consider it one layer. Let's see. I think that's it. So let me go back to the presentation and try and wrap this up. I know I'm a little bit over time, and I appreciate everybody staying on. I must have been saying something that was useful. So one of the things that, you know, with this layer protection analysis and layer protection analysis tool, it's part of that full integration that we're working on, and you see how data flows from the PHA into the Lopa, and I think that's really the path forward. As I mentioned, we're finalizing a database that will allow you to link initiating events to frequencies that will allow you to link probabilities of failure for IPLs to the database. And there's going to be an exida database as well as a user-definable database. So you as a user can define your own database, and you can keep that within the project, or you can keep it as a separate entity on your machine and share with your colleagues. And you will be able to link from that and copy the data from those databases. And that will be pretty powerful, and it's going to be in a similar way as we do exSILentia, as we do Silver in the exSILentia suite, where you have a drop-down list with specific devices, and we anticipate that we will be adding some manufacturer-specific devices to these IPLs as we go forward. So there may be some relief devices that we have specific data for that we can add to that database. So now the overall concept of this integration is consistency, the seamless data flow. We see the hazard scenario basis, and then back to the one question that I had earlier. Do you have to have multiple initiating events or not? It's all up to you. You can decide how you want. Some people really put all their initiating events and lead to the same consequence in one hazard scenario, and other people have the policy of not doing that. The tool is very flexible in that regard as to what you can do. I see here a wonderful comment here that someone really likes what they're seeing, and I'm happy to hear that. So when is it released? That's a good question. The platform is released. exSILentia 4 platform is released. The PHA module is released, and the Lopa module are released. So the two modules that I showed you today, they are available for purchase right now. The next modules, the SRS and the Silver module, that they're currently, SRS is in internal beta, maybe you should call it alpha, but it's in beta stage. Is a significant extension of what we had in exSILentia 3, and the Silver portion is currently worked on. There's quite some you can call them requirements and requests from customers for some changes that we're implementing. I think it's I'm very excited about it. I hope the users are as well. All right, I'm 10 minutes over time. I still appreciate that people are here. Thank you very much for listening. If you have any questions, you can email info@exida.com, and we will. They will make sure the question will get to me. info@exida.com. One more question here. There's quite a number coming in here. Is that I talked about this, the details about the books where data can be found for layer protection analysis. So the American Institute of Chemical Engineers, the Center for Process Safety, Center for Chemical Process Safety, has an initiative called PERD, P-E-R-D, Process Equipment Reliability Data. And they have published a book in the 90s, I think, with some probabilities of failures and frequencies. And they're in the process of publishing a new book with specific initiating event frequencies and protection lines. That would be a good source. Another source is a book, Loss Prevention in the Process Industries, by a gentleman called Lees, L-E-E-S. That may be, let's see, I'm drawing blank on anything else. The exida equipment database for the Lopa tool will be one. I think that's everything that's coming to mind right now. With regard to this presentation, there's a recording, and we're going to have this recording posted on our website, and you will be provided a link to it. And I know our marketing group is very active on LinkedIn and things like that. So there's probably going to be a comment that yes, you will be able to look at this later. So thank you very much for dialing in. I appreciate the questions. There were very good questions. The remainder slides here, just where is exida, what are our products, and if you have any other questions. So I think we covered that pretty much. Thank you very much for dialing in. And if you're interested, this afternoon, 4 p.m. East Coast time, there's a second session. Feel free to dial in at that as well. And if not, talk to you on the next webinar. Take care and bye-bye.